Okay, so welcome back from the break. We're going to get started with one of the science sessions on teleconnections. In particular, the title of this session is Advances and Challenges in Understanding and Predicting Climate Teleconnection. And it's a topic that emerged in our last meeting with the US CLIVAR Science Steering Committee in January. So there are a few guiding, first let me introduce myself, I'm sorry. My name is Emanuele Di Lorenzo, and I'm co-chair of the POS panel. And I organized this session together with Dan Vymont, who's sitting here in the first row, who's still eating his breakfast. Very good. Anyway, we had a few guiding questions for this session, which I'm going to briefly read. The first one is, which observation and modeling approaches are required to establish robust relationship between teleconnection dynamics and changes in the mean state, for example, decadal and climate change? The second question is, how predictable are the impacts of teleconnections? And here, when we say predictable, we also want to quantify the sources of uncertainty. And one example could be ENSO on regional and coastal systems, for example, extreme events, droughts, marine heat waves. Are these impacts being influenced by global climate change? The last and third question is, which approaches and methods are best suited to diagnose teleconnection dynamics and impacts in climate models and perform comparisons to observations? So with this in mind then, the session is really centered around three main topics. The first topic in terms of climate teleconnection is the sensitivity to mean climate state and decadal variability. The second topic is about
the conference has been muted.
The impacts on regional and coastal systems. And lastly, the third topic is really about the diagnostics, methods to diagnose climate models and compare with observations. So these are the kind of three overarching topics. And with that in mind, we have organized a session around 4 speakers that are going to essentially touch on several aspects of these different topics. Our first speaker is Alyssa Atwood, which will talk about high-latitude teleconnections to tropical mean climate, observations versus model. And I think in the newer version, there's also a Paleoclimate plugin in terms of data. The second speaker is Daniel Swain, talking about teleconnection and regional impacts under anthropogenic forcing. The third speaker is Antonietta Capotondi, who's going to talk about ENSO diversity, teleconnections, and impacts. And last, Samantha Stevenson, methods to quantify uncertainty in coupled climate model teleconnections. At the end of the session, we'll have a little brief panel discussions. And so, first speaker, please come to the podium. Alyssa.
So yeah, I'll be talking about high-latitude teleconnections to tropical mean climate with a specific focus really on paleoclimate observations or paleoclimate proxy records, as these can provide novel insight into teleconnection patterns for which we don't really have any modern analogs for, and recognizing that there's value in understanding these teleconnection patterns in an increasingly uncertain future. So this is work that I've done primarily through the support of the NOAA CPAS Climate and Global Change postdoctoral program, and with my collaborators, John Chang, David Battisti, Cecilia Bitts, and Julian Sachs. So primarily, part of what I'll be focusing on is looking at these rapid variations in temperature in the northern hemisphere that happened over the last glacial cycle. These are called Damsgaard-Oeschger events, and paleoclimate records indicate that temperature variations changed by as much as 15 to 20 degrees Celsius over a period of just a few decades, at least over Greenland, and that these temperature variations had a hemispheric scale. Some of these stadial events were also associated with ice-rafted debris in the North Atlantic, and those are called Heinrich events. So that's up to 2/3 of sort of the magnitude of glacial, interglacial temperature variations. And in sync with these northern hemisphere temperature variations, we see evidence of large changes in tropical hydroclimate sort of in tandem with these events. So this is just showing the oxygen isotope record from the Greenland ice core in blue there. And then looking at 2 records of hydroclimate from the Arabian Sea and Cariaco Basin just off the coast of Venezuela that show evidence for drawing in northern hemisphere monsoons and regions of sort of the northern reaches of the ITCZ coincident with these cold events. And indeed, there's evidence sort of distributed across the tropics that also show evidence for wettening in the southern tropical regions. And that these hydroclimate changes occurred with sort of in sync with these northern hemisphere cooling events, so such that there's evidence or suggests that provides evidence for an atmospheric teleconnection between them, such that they happened very rapidly. So the leading cause for these abrupt events is thought to be changes in the Atlantic thermohaline circulation, such that a shutdown of the thermohaline circulation caused dramatic cooling or reduction in the northward heat transport in the ocean that led to cooling in the North Atlantic that then spread across the northern hemisphere. Sort of myriad of climate modeling simulations suggest that when you impose freshwater flux into the North Atlantic to shut down the AMOC, you do see sort of this hemispheric scale cooling that occurs that creates the sort of interhemispheric pattern of surface temperature. And that interhemispheric pattern shifts the tropical Hadley circulation such that you see a weakening of the northern hemisphere monsoons and a strengthening of the southern hemisphere monsoons, and the southward shift of the intertropical convergence zone in the Pacific and Atlantic basins. And there's also some work that's been put forth by John Chang and others that have suggested that once you shift the ITCZ south, which leads to a strengthening of the northern Hadley cell and a weakening of the southern Hadley cell, you also see concomitant changes in the wintertime subtropical jets, which are driven by the angular momentum transport from the Hadley circulation, so that when you shift the ITCZ south, you strengthen the wintertime subtropical jet in the northern hemisphere and weaken it in the southern hemisphere. And just looking at these changes in the ITCZ, this figure is showing changes in the tropical precipitation centroid, which is a measure of the ITCZ changes after a one sphere drop freshwater flux has been imposed into the North Atlantic in a variety of different models and coupled climate models. And so you see a lot of variation in sort of the spatial characteristics of the southward ITCZ shift, particularly in the eastern and central Pacific and in the Atlantic basins. And this is likely, at least in part, due to the large tropical mean state biases that exist in these models. So moving into sort of the case study that I'd like to focus on is the 8200 BP event, which is the most recent occurrence of this type of abrupt event. You can think of it as sort of a mini Heinrich event, but that happened where not during the last glacial cycle, but within the Holocene. And so this has been associated with about 160,000 cubic kilometers of glacial meltwater from the remnants of the Laurentide ice sheet that poured into the Labrador Sea around 8,000 years ago. And proxy records indicate that this salinity perturbation was sufficient to weaken the deep water formation in the North Atlantic and weaken the Atlantic meridional overturning circulation. And there's sort of a compilation of surface temperature reconstructions from across the globe that indicate that this event was associated with changes in or cooling in the northern hemisphere high latitudes, most pronounced in the North Atlantic, where we see about estimates vary from 2 to 6 degrees Celsius of cooling over Greenland, about a degree cooling throughout Europe and the Mediterranean, and that cooling reached the tropical Atlantic. There's also an abundance of hydroclimate records from across the tropics that indicate that tropical hydroclimate or tropical precipitation shifted south in association with this event. So this is just showing a compilation of records, primarily oxygen isotopes from speleothem records in northern hemisphere monsoon regions. In the top two panels, the top one is from Dongye Cave in China, and the second one is from Oman. And then we see evidence of a strengthening of the South American monsoon, which is the third record down is actually a speleothem record from Central America, which also shows drying. And then we see evidence of a strengthening of the South American monsoon from a Brazilian speleothem record, as well as evidence of a strengthening of trade winds across the north coast of Venezuela, producing increases in upwelling-driven productivity there. And then finally, at the bottom there is a hydrogen isotope record that I worked on for my PhD that looks at, it's from the Galapagos Islands, that suggests that rainfall in the Galapagos Islands was wetter during this event. So if we just look at these sort of in a compiled map here with a few other records, here are those same proxy records and then overlain with observed climatological precipitation from sort of the seasons in which the ITCZ is at its northernmost and southernmost location. And what we see is particularly in the Eastern Pacific and over South and Central America, we see evidence of southward shift in the ITCZ in this region during this event. And in addition, there's evidence of decreased El Nino activity in the tropical basin during this time. And this is coming primarily from two recent records, which I'll just go through briefly. The first is coming back to this Galapagos Lake record, or an additional sort of subset of the proxy records this is from El Junco Lake, which is the only permanent freshwater lake in the Galapagos Islands, as well as from a speleothem record from Borneo in the far western Pacific. And this map is just showing the composited rainfall anomalies during the most recent 3 strong El Nino events, showing that those are good places to look for El Nino rainfall reconstructions. So this biomarker record from the Galapagos Islands was, it's looking at the concentration. It's plotted in red here, and it's the concentration of a biomarker that's produced by a green algae that blooms during El Nino events in this lake that's tied to extreme rainfall, sort of Eastern Pacific El Nino events, I should say. That's tied to extreme increases in rainfall and sort of decreased nutrient concentrations in this lake. And so you see evidence of around 8,000 to 8,500 years ago, which coincides with this event. We see evidence of very low concentrations of this biomarker, which suggest decreased frequency or intensity of El Nino events during this time. And that's corroborated by a grain size record also from this lake basin that was put out by Jessica Conroy, that's plotted in gray here, that shows, or that suggests that, that sort of these extreme Eastern Pacific rainfall events that wash these large coarse grain material into this lake was also decreased at that time. And then moving into the Western Pacific, this is a record that was put out by Seng Chen and collaborators last year that looks at these sort of high resolution time slices of oxygen isotopes in a speleothem record from Borneo that cover the Holocene, but one of these high resolution slices coincides or encompasses the 8200 BP event. And so we see sort of the realization of this event as the top plot there is showing the raw oxygen isotope values, and the bottom figure is showing the 2 to 7 bandpass filtered time series, or the ENSO band. And so we see this event as marked by very depleted conditions, very depleted isotope values in this record. And then if we just look again at the sort of 2 to 7 year bandpass of that time series, the 60 years at and after that extreme enrichment event is the lowest 60-year, has the lowest variance of any 60-year period in this record. So that is sort of providing additional support now from sort of the two extremes of the Pacific Basin for reduced ENSO variability associated with this event. So taken together, again, these proxy records are really indicating a southward shift of the ITCZ, particularly in the Eastern Pacific Basin, and reduced ENSO variability. And so how are these two things how may these two things be connected? And while we have sort of a good theoretical and modeling framework for thinking about the southward shift of the ITCZ, there's not as much theory to sort of bolster the idea of how the ENSO variability may be related to that. And so to sort of look into this in more detail, I performed simulations with a community Earth system model with prescribed freshwater input into the North Atlantic to shut off the AMOC and look at sort of the global response to this event, particularly in the tropical Pacific. And so this is just showing on the right here is the sea surface temperature changes after, so within about 20 years, the AMOC shuts down. This is a spear drip of freshwater input into the sort of distributed across the North Atlantic. And so you see extreme cooling in the North Atlantic that sort of wraps in the C-shaped pattern into the tropical Atlantic. And you see evidence of that cooling actually propagating into the tropical Pacific. And in association with that and the surface pressure changes that coincide with that, you see increased in the northeasterly trade winds in the northern Atlantic and northeastern Pacific Basin. And so this is showing the precipitation changes that occur in this model. And what we see, and then sort of overlaid on top of that are the proxy reconstructions. And so what we see is we do see a southward shift of the ITCZ of tropical precipitation in this model as expected, particularly you do see that over South America and over the Eastern Pacific. And while there's not sort of, so there's general agreement, I would say, in this sort of dynamical context of the precipitation changes over the East Pacific Basin. And in association with the southward shift of the ITCZ in the Eastern Pacific in this model, what we also see is strengthened zonal wind stress. And so the unfilled contours now are the change in the zonal wind stress. And so the zonal wind stress maximizes where the northern branch of the ITCZ shifts from, as well as you see a secondary maximum right on the equator. And that ends up being important because it's associated with relatively large subsurface warming along the equator. So this is just showing the subsurface temperature changes in the upper ocean along a 2 north to 2 south slice of the tropical Pacific. And so you see maximum warming sort of right along the thermocline as indicated by the 28-degree isotherm in the bold there. And so this is showing that the thermocline in the tropical Pacific is deepening and diffusing under the freshwater hosing. And we can think of these two things as being related, the southward shift of the ITCZ and the change in the zonal wind stress and the subsurface warming due to the changes in the wind stress curl. And so again, coming back to the secondary maximum of the zonal wind stress that's on the equator, what this sets up is a dipole pattern in the wind stress curl off the equator. And so you have a negative wind stress curl anomaly just to the north and a positive wind stress curl anomaly just to the south. You can think of as through spear drip transport and bringing in warm water into the equatorial Pacific region. And so in agreement with proxy reconstructions in this model, we do see evidence of decreased ENSO variability. This shows a 20% reduction in the variance of Nino 3 SST anomalies under hosing in this model. And I performed a series of simulations with an idealized offline model of the tropical Pacific that suggests that it's this subsurface warming, this diffusion and deepening of the thermocline, as well as the large-scale tropical Pacific cooling that's stabilizing the coupled ocean-atmosphere interactions that give rise to this decrease in ENSO variability in this model. So again, those mean state changes are really what's important for the tropical Pacific mean state changes are what's important to ENSO variability. And so this is just kind of the schematic that lays out the North Atlantic hosing that gives rise to the southward shift of the ITCZ that in this model occurs in the eastern equatorial Pacific that sets up the subsurface warming through the changes in the wind stress curl and leads to reduced ENSO variability. So this provides some consistency between the proxy records and this model simulation. What I would like to point out is this is not a universally consistent result for how ENSO responds to weakening of the AMOC. There have been a number of studies, particularly most of which use sort of the PMIP, the CMIP3, the older generation of models, that show a wide variety of responses. Most of the PMIP3 models actually showed an increase in ENSO variability under hosing, but more recent studies have showed everything from no change to increase to decrease. So this is likely, again, tied to the large tropical mean state biases in this model and how the precipitation changes or the climatological precipitation and SSTs are represented in these models. But at least in the CCSM4 here, we are seeing some consistency between the proxy records and the model simulations. But ultimately, we need more high-resolution records from the tropical Pacific to really understand this event, and we can't really move past that without, or get to our next level of understanding without having more data to go off of. So just to conclude, proxy records can provide novel insight into teleconnection patterns for which there is no modern analog. One such climate configuration or climate event is the 8200 BP event, which is the most recent period of abrupt climate change. And proxy records indicate that the ITCZ shifted south in the eastern Pacific during this time, and that ENSO variability was weakened. And these changes are reproduced in the community or system model under North Atlantic freshwater forcing, but the tropical Pacific response is model dependent, likely due to these tropical mean state biases, and ultimately more high resolution proxy records are needed to better understand this event. Thank you.
Questions. One is that you imposed one swear drop over a 100-year period. How realistic is it in terms of magnitude? The second of all, I'm a little bit surprised that the response that you got in the Pacific, you have an AMV-like pattern in the Atlantic Basin, and that in turn creates a negative phase of the PDO in the Pacific, and your SST is showing the positive phase of the PDO. Would you comment on that difference?
So let me start with the first question. The sort of realism of the forcing. So certainly we don't expect that, or the proxy records don't indicate that associated with the 8200 BP event was a complete cessation of the AMOC, which is what was imposed in this model simulation. The idea behind the sort of idealized framework for the modeling simulation was to provide a large enough forcing and long enough statistics to really understand, to maximize the signal to noise and thinking about the ENSO response. So with its applicability to the 8200 BP event, we'd have to think about a moderated response to that. Okay, I think you need to repeat the AMV.
The second question is that in the idealized AMV experiments, or if you look at the AMV-related studies, the positive AMV anomaly tends to essentially create a negative PDO signal in the Pacific Basin. In your experiments, you get actually positive AMV pace in the North Atlantic,
yep.
but you essentially see a positive PDO, not a negative PDO.
Okay.
I'm just trying to understand why that difference is occurring.
Yeah, I don't have, I would be interested. I would be very interested in that, and I don't know.
My question is follow that same line. So when you look at the model response to the shutdowns circulation, okay? You only look at the East Pacific Ocean, right? What about the West Equatorial Pacific Ocean? The temperature increase or decrease? So I think that when you see the ENSO variability intensity change, so should you look at the West warm pool too, and the thermocline. So have you look at this response in the West Equatorial Pacific Ocean? That's my question.
Are you talking about in the models?
Yeah.
Yeah. So in CSM, the Western Pacific, I mean, you saw sort of that deepening and diffusion of the thermocline happen pretty much across the Pacific Basin, except for in the far Western Pacific. But throughout the sort of central and eastward edge of the warm pool, you do see that subsurface warm anomaly occurring. In the surface temperature response, you saw, there was. Yeah, the cooling extended. It was, had highest signal in the Eastern Pacific. It extended into the Central Pacific, but there's not much of a surface temperature change in the Western Pacific, in the far Western Pacific. Yeah, but I would argue that for at least as the idealized model is suggesting, what's really important to ENSO is what's happening in the Central Pacific, particularly with the subsurface temperature variation.
Thanks, Alicia, very much. Our next speaker is Daniel Swain, talking about teleconnections and regional impacts under anthropogenic forcing.
It's really great if you could use your mouse. Okay. And there it is up there.
Perfect. Thank you. Hello. First, I just wanted to thank the committee for the invitation to speak here today. And as mentioned, I'm going to talk about teleconnections and regional impacts in a warming climate. So just a really quick outline. I'd first like to use California as a case study for regional impacts, given the recent transition from severe multi-year drought to flood and the El Nino in between that didn't really produce the effects that a lot of people had expected. The importance of embracing complexity in regional impacts, not just in the way we do our analyses, but also in the way we think about the physical processes involved. And then close with some thoughts on considerations in a warming climate, particularly the potential for non-stationarity in impacts and the potential for essentially novel predictors in a very different Earth system. So I think as many people in the room are probably acutely aware, California just experienced a very intense multi-year drought between 2012 and 2016. And the proximal cause of the extreme dryness and warmth in California was the seasonal and really multi-year persistence of a ridge of atmospheric high pressure, particularly pronounced in the middle troposphere. And there is, at this point, there's been a lot of work on this. There's now evidence for both random internal and also ocean-forced causes for this ridging in the East Pacific over these years. We now know that these sorts of really extreme events can arise randomly through internal variability. There does not necessarily have to be a forced trigger for these, but in many cases, warm SSTs in the tropical West Pacific contribute either to the amplitude or the initial formation of these persistent ridges. Obviously, these two things can act in concert as well. And there's still some discussion about whether there may have been some role for extratropical feedbacks. I think at this point it's pretty clear that the initial trigger for the ridge that caused the drought was not extratropical ocean temperatures. But once the ridge was there, extraordinarily warm extratropical temperatures in that ocean region developed and persisted for a few years, and there may have been some positive feedbacks in that system. And I think what's interesting to note about this sequence of events in California is not only did it have large impacts on the ground, and not only was it a high-profile event from an atmospheric science perspective, but the multi-year persistence and the subsequent evolution over these few years to flood was not really well captured by seasonal forecasts, and particularly by the operational multi-model ensembles that NOAA uses to make its seasonal forecasts. And this is interesting. And I have up on the screen here on the left is just an animation just showing the predicted precipitation anomaly using September initial conditions for each of the winters during the sequence of events that I'm talking about. And the multi-model ensemble actually did capture the onset of the drought, the first year or so, showing relatively dry conditions in most of California. But that subsequent persistence and then the eventual transition just this past winter to extraordinarily wet conditions really wasn't there. And that's particularly interesting because in the mix there, as I mentioned, was that very strong El Nino event during winter 2015-2016, which a lot of people thought would have sort of given a boost to predictability, at least during that year. So I think there's a few relevant questions that arise from this. And the first is whether a significant portion of this may have actually just been because the causes of the sequence of events was fundamentally unpredictable. If it really was just a product of random variability that we really shouldn't have been able to foresee even with a perfect model. And the other possibility on the other end of the spectrum is that all of it was fully linked to traceable Earth system processes, but that for some reason our operational multi-model ensembles either didn't get those boundary conditions correct or then didn't get the coupling between the real world and what actually happened correct. And these are not mutually exclusive possibilities. In fact, the reality probably lies somewhere in between. But I think it sort of is interesting to pose these as sort of alternative hypotheses. The case of El Nino 2015-2016 and its regional impacts along the West Coast I think is especially interesting because it was really well predicted from an oceanic standpoint. The extreme warmth in the eastern equatorial Pacific Ocean was really part of all the model forecasts that were in place months in advance. And as you can see on this just a two-frame animation on the left of the screen here, showing just the geopotential height anomalies composited for the 82-83 El Nino event, the 97-98 El Nino event, so the two previous strong events in our recent observational record, and then just what actually happened in 2015-16. And what you can see if you squint a little bit is that it's essentially the overall atmosphere looks pretty El Nino-like in both of these, with a profound deepening of the Gulf of Alaska low and high heights in the tropics. But if you really focus on the West Coast and California in particular, you can see that the regional differences between sort of the canonical El Nino teleconnection there and what actually happened in 2015-16 is really profoundly different. And that, as I mentioned, that had really large impacts on the ground. Along the West Coast, California ended up being relatively dry during this very strong El Nino event, and yet the Pacific Northwest was extraordinarily wet, in fact, record wet in some places. And what I just wanted to highlight, and this actually comes from a recent paper by Cohen et al., just showing that the observed, the blue line there, precipitation for Seattle actually was more than double that of the most extreme ensemble member in the seasonal forecast for that season. And in Los Angeles, the observed precipitation fell below the driest ensemble member, despite this really strong forcing that we were getting from ostensibly from El Nino in that year. So I think that's pretty interesting. And I think all of this sort of gets at a broader question, and which is how do we know what we think we know about regional teleconnections associated with, I'm using ENSO as an example, but even in a more general context. And I think there really are some challenges because our existing observational record is often too short to make really robust conclusions just based on a sample size of, for example, of strong El Nino events in the recent observational era, 2 or 3. that makes it challenging. And so often what we then turn to are these large ensembles of climate model simulations that can yield much larger, if artificial, sample sizes, and also give us higher confidence in the physical insights that we can draw, given the potential to do really, really fundamental process-based studies. And I think a nice illustration of this is the graphic up on the left, also from a paper in 2016, showing the strong similarity between the precipitation teleconnection for El Nino events of different magnitudes relative to observations. And essentially what it's saying is there actually isn't that strong of a teleconnection for any event except for the really strong ones, but when you do have a strong one, what you see in the real world is relatively similar to what you get in the large multi-model ensemble. And yet that's still not what happened in 2015-16. And so one of the questions that I get a lot as somebody who is in California and talks a lot about El Nino and extremes is, should that regional forecast failure, should the fact that it didn't rain that much in California during the last really strong El Nino event change our priors? Should we just totally throw it all out the window and say that El Nino doesn't mean anything anymore in California? And I would argue that the answer is probably no. If we had those same conditions again, I think most people would probably agree that there's a good reason to make the same forecast again in the future. That being said, I do think there are several factors that complicate our deeper understanding of regional impacts of teleconnections that we derive from large climate model ensembles and climate simulations in general. And one of these is the possibility that in some cases distinct climate regimes can arise exclusively from internal variability, both in the real world and in the simulated ocean atmosphere world. And there's some interesting example of this. You may even hear about this more later today. There's evidence that there are actually distinct but essentially stochastic El Nino eras where the character of ENSO is either particularly extreme in magnitude with wide swings between extreme El Ninos and extreme La Ninas, or spatially different in the sense that there are eras where El Ninos tend to be east basin centered or more central basin centered. And these can arise completely without external forcing at all in these simulations. And a related issue is the potential for state dependence in the response to forcing. And I think a really fascinating example of this are a lot of the studies that are coming out on the relationships between Arctic sea ice loss and mid-latitude variability, where a number of these studies have historically suggested that the response to sea ice loss really may depend on the Northern Hemisphere SST pattern. And I think a nice illustration of this is from Overland et al. 2016, which is the graphic up on the screen right now. And that's just illustrating that in two experiments that are identical, or the same amount of sea ice is removed in the same spatial pattern, but the mid-latitude SSTs are different, you either get a robust mid-latitude response or you don't, using this exactly the same model. And so that just is an illustration of how difficult it may be in a lot of cases to extract what the regional signal might be to these teleconnections or to remote forcings like this. And so I think I might return a little bit to the California example to illustrate another point about the importance of embracing spatial and temporal complexity in analyses and metrics. And one of these is that we broadly expect that the Hadley cell is likely to expand as the globe warms, potentially in an asymmetrical fashion, but in general, there will be subtropical drying associated with this. And along with that, a poleward shift in the jet stream, along with wettening on the poleward flank of that shifting jet stream. What that means for so-called Mediterranean climate regions, not just in the Mediterranean basin itself, but in other mid-latitude west coastal regions that have similar climates, precipitation mostly declines in climate model simulations for the 21st century. But what's really interesting is that this does not hold true in all regions and across all seasons. And I think one of the classic examples of this is the fact that the most climate models simulate an equatorward shift in the winter mean jet axis over the North Pacific Ocean. And that has really profound implications for California in particular, because that is the rainy season when about 80% of the precipitation annually actually falls. So if you're worried about hydroclimatic variability in California, that shift that is contrary to the mean shift is actually critically important. And as I mentioned, one of the net effects of this is that despite relatively modest simulated precipitation changes in California's future, maybe slight wetting on average or little change relative to the natural variability there's a really large increase in projected extremes, and not just on the wet side, but also on the dry end of the spectrum. And what this appears to be linked to is the increasing frequency of extreme ENSO events, El Nino and La Nina events, not just the increasing trend towards a slightly El Nino-like mean state in the future where the eastern tropical Pacific Ocean warms more than the west. And it turns out that how you do the analyses within specific regions like this California example has very large implications for decision-making and climate adaptation issues, because one, if you think about the future as being slightly wetter due to the more El Nino-like mean state, which is a valid way of interpreting climate model simulations for the future, or you frame that exact same data and those exact same simulations in a way that you discuss the large increase in extremes, owing to a more ENSO variability with a slight tilt towards strong El Nino events, those are two very different outcomes apparently, but they're actually both consistent with one another, and it's really critical to be talking about both of them, both from the physical understanding standpoint and also from an impact standpoint. So I think the broader lesson there is that embracing that the spatial and temporal metrics that can account for that sort of complexity is really critical. And there's another issue as in a warming world is whether or not we should expect teleconnections and their impacts to be time stationary. And it's often assumed that the underlying processes, at least for most of these fundamental teleconnections, are themselves stationary. And there's definitely a lot of evidence that existing modes of variability in the atmosphere are going to be easier to excite than totally novel ones. But for regional impacts, I would argue that the interactions with the mean state, even if the teleconnection processes themselves are essentially stationary, can really affect outcomes. And part of that is because as the atmosphere warms and as a lot of things change pretty dramatically, the position of the continents doesn't change. The location of the Earth's major ocean upwelling zones and cool ocean patches aren't going to change either, and in many cases, it's these zonal asymmetries that define things like the land-sea thermal contrast, which there's already been some work looking at, and since it's expected to increase, that may be really important in regions where there's pre-existing zonal asymmetries in the structure of atmospheric flow, particularly in the oceanic storm track regions. And what's interesting is what's going on along the west coast of North America in future simulations is sort of at that margin of a storm track region. And so that might be one of the examples of what happens when the mean state changes in a way that's different from the regional changes that are going on. I think I just wanted to close with a few thoughts on the potential for emerging teleconnections. And there has historically been a very strong focus on the tropical ocean as a predictor of mid-latitude atmospheric variability, and for good reason. And there's a lot of places in the world where there's no better or really no other meaningful predictor other than ENSO, as far as we understand it now. But for example, the Arctic is really changing rapidly and profoundly. I don't think I need to repeat that to anyone in the room here. And at some point this century, there's going to effectively be a new ocean basin for a small portion of the year at least. And so clearly that will exert different forcings than we are used to historically. And another thing, in addition to that has been a little bit less discussed, is the potential for warming to induce continental scale soil drying and vegetation shifts. And That's, I would say, important not just from a local moisture balance perspective, but also because of the potential for feedbacks to large-scale circulation. And I would argue that these are difficult but critical challenges, not only because they affect our physical understanding, but because there may actually be, in the future, opportunities for increased predictability as some of these emerging predictors become potentially more important. So I'll just skim through the key points, leave them up there, and close with that.
Our next speaker is Antonietta Capotondi. She's going to talk to us about, again, ENSO diversity, teleconnections, and impact.
Thank you, and thank you very much for inviting me to speak here. Oops. So I can.
Hold on. Sorry.
Okay, and I can just use the arrows. Yeah. Okay. So ENSO diversity has been associated with different teleconnections and impact, and this is one of the reasons of the popularity of this topic in the last 10, 15 years. However, due to the large level of noise in the climate system, as well as the small sample size that we have for events of different types, there is a lot of uncertainty about the differences in the different impacts of different types of events. So what I would like to do today is just provide a brief review, but also outline ways in which we can methodology or approaches that we can use to identify or to isolate the predictable component of the system that we are interested in, and how that is influenced by the tropical conditions. I will be focused on the US West Coast region, and I will be looking primarily at sea surface temperature and sea surface height anomalies. These are quantities that are very important per se for the communities living along the US West Coast, but they are also very key quantities for the rich marine ecosystem of the US West Coast. So ENSO diversity has been primarily identified by differences in spatial pattern, essentially characterized by sea surface temperature maxima at different longitudes. And this is illustrated here by the 1997-98 and the 2002-2003 El Niños. The first one had large anomaly in the Eastern Pacific, so this is a typical or canonical Eastern Pacific event. And the second one with the larger anomaly in the Central Pacific has been considered a Central Pacific event. Of course, there are differences in impact that we can that are obvious. So in the first case, close to the eastern boundary of the ocean, we have very large anomaly, and we can imagine that can drive intense rainfall and floods in the Eastern Pacific region. In the second case, in the case of the Central Pacific events, the anomalies near the coast are much weaker, and so for those regions, the conditions are almost neutral. So Central Pacific events have also been associated with reduced precipitation over India, northern and eastern Australia, have also been associated with changes in the atmospheric circulation in the southern hemisphere, and also temperature anomaly of Antarctica. However, especially when we look at the different differences in impacts of these different type of events on quantities, for example, like temperature and precipitation of a different region like the US, there is really a lot of uncertainty, very relatively small statistical significance in the values that we have. So the US West Coast is an interesting area because we know that ENSO is a very important source of predictability for that area. However, just also as we have seen in the previous talk, as far as precipitation is concerned, different events sometimes don't have the impact that we anticipate, and so there is also a lot of uncertainty in this. And it's unclear whether this arises from the diversity of ENSO events or also for the large internal atmospheric variability. So the way ENSO influence the U.S. West Coast is through both oceanic and atmospheric pathways. So the oceanic pathways is mediated by coastal Kelvin waves, which propagate from the equator along the coast. So this is vividly illustrated here by this altimeter, by this surface height image from altimetry at the end of December of 1997, so at the peak of this strong El Nino event. So we can see, let's see, I'm trying this. Along the equator, we can see negative anomaly in the Western Pacific, positive anomaly in the Eastern Pacific, so associated with this change in the tilt of the thermocline, and then this positive anomaly continue along the coast with the decreasing of short scale, and at some point we lose them. So this is a pathway that whose efficiency is still unclear, partly due to the difficulty or actually measuring observing the waves, and also the difficulty in modeling realistically these wave processes, which are also strongly affected by boundary processes like friction. So from the atmospheric viewpoint, the main influence of ENSO is in the modulation of the Aleutian law. So we see here this large, so this is the mean conditions in sea level pressure, characterized by this by the Aleutian law in the North Pacific and the subtropical high in the subtropics. And this is associated with this circulation, which is cyclonic around the Aleutian law. And the winds, if we look at the winds along the coast, they are downwelling, favorable winds in the Gulf of Alaska, and upwelling favoring winds along the California coast. So during El Nino, the Aleutian law, this is an example for the 1982-83, the Aleutian law deepens and also gets displaced further east and south. And so if we again focus along the coast, this leads to an increase in this in downwelling in the Gulf of Alaska, and then a decrease in the upwelling favorable winds along California. So although all El Nino events tend to have the signature in the Aleutian law, the intensity, the exact position, the exact structure vary from events to events. And again, this is unclear whether this is due to changes in the details of the sea surface temperature pattern along the equator, or also to the large atmospheric noise. So if we, in an attempt to try to understand possible differences between these two types of events along the California current, along the U.S. West Coast, we can compute composites for EP and CP events. And this, I've done this here for a long control simulation of the CCSM-4 and also for observations on the right. And basically, we see that the signature of this different type of event along the coast is not very different in the two cases. It's just much weaker in the case of Central Pacific event. And it's unclear if this is due because of the spatial structure of the events, or just because the events in the Central Pacific tend to be weaker. So in order to move forward, we can actually, instead of trying to understand what different patterns produce, we can rephrase the question in a different way. And maybe since we're interested in these quantities, sea surface temperature and sea surface height along the U.S. West Coast, we can ask what are the optimal tropical conditions that maximize this quantity. So the way we are going to do it today is by using a combination of multiple linear regression and singular value decomposition. So as you can see here, if we're interested in a quantity y at a leg tau, and this quantity is related to a quantity x at an earlier time through this operator h, we can determine the x as the leading singular vector, right singular vector of h. And we can determine h by multiple linear regression. So I'm going to apply this methodology to this long pre-industrial control simulation, and I'm going to construct indices for sea surface temperature and sea surface height as by averaging these quantities in this narrow band along the U.S. West Coast, extending from approximately 30 south to 55 north. So in this framework, Y actually is a scalar, is one of these coastal indices, and X is the tropical Pacific sea surface temperature in the 25 south, 25 north band. So the indices themselves, this is a busy slide. So on the left, we see this coastal surface temperature index on the top in red, and the sea surface height index in blue on the left bottom panels. And just by visual inspection and also with a more formal leg correlation analysis, we see that indeed we find a pretty large correlation with the ENSO indices. I'm looking here at Niño 3 and Niño 4. So for sea surface temperature, we have values close to 0.5 for a leg of approximately 7 months, and the sea surface height actually has larger correlation with the Niño indices above 0.6 at the legs of approximately 5-6 months. So what about our optimal tropical conditions? So we can start by sea surface temperature. So we are taking this index along the coast, and using the methodology that I've outlined before, we find this pattern for, this is this optimal precursor pattern for sea surface temperature anomaly along the coast. So you will notice that this pattern doesn't really look like a mature ENSO pattern. Instead, it has some features like this positive anomaly from Baja California extending southwestward toward the equator, which is reminiscent of the North Pacific meridional mode. There are also positive anomaly hugging the coast on the that are reminiscent of the South Pacific meridional mode. We see this positive anomaly that are along the equator that are associated with the deepening of the thermocline there that precede the full mature stage of El Niño. So we can do the same also for sea surface height, and if we compare it with the previous pattern, actually they are quite similar, except maybe for the amplitude in some regions. So we are going to use for the following analysis the sea surface temperature pattern. And once we have the pattern, we can compute a time series associated to this pattern, which will be called the optimal precursor index, by projecting the sea surface temperature at each time step on that pattern. And so we find these black curves in these two panels. These are just the two 80 years examples. They indeed show some good correspondence with our coastal indices, the sea surface temperature in red and the sea surface height in blue. And we can also notice that there is some evidence of some longer frequency variation, decadal variations. So if we look at the correlation now of our optimal index with the coastal indices, and again here the optimal index leads, we see that correlation for sea surface temperature are about 0.5 in a very broad range of legs, and the correlation with sea surface height are even higher and higher than 0.6, again all the way to legs close to 12 months. It's interesting to compare this correlation pattern with what we've seen before with, in this case we are using the Niño 3.4 index. So we are correlating here the Niño 3.4 index with the coastal indices. And for sea surface temperature, our optimal precursor pattern is always higher. For sea surface height, we have that for legs close to 3-4 months, we have similar value, but otherwise our optimal precursor index gives us more predictability to longer legs. And it's also interesting to look at the relationship of our coastal precursor, of our optimal precursor index with the Niño 3.4. This is the black line, and we can see that the maximum leg is achieved when the optimal precursor index actually leads the Niño 3.4. So we can see as this pattern that we have identified is at the same time leading to ENSO events as well as these coastal impacts. So we've just focused on the average condition along the coast. So what are the concurrent conditions over the whole basin? So this is our coastal index for sea surface temperature. So I can construct a composite by looking at the times when the index is above a certain threshold. Here I'm choosing one standard deviation. And I see that when the values along the coast are high, this is associated with negative anomaly in the central North Pacific, extending all the way toward the coast, and El Niño-like condition near the equator. At the same time, sea surface height also has maxima along the coast and negative anomaly, so shallower thermal structure in the central and western North Pacific. And we see the dipole pattern along the equator. We also see this positive anomaly just north of the equator, around 13 north, associated with the westward propagation of Rossby waves. And if we look at the sea level pressure, we see this very large negative anomaly, this deepening and displacement of the Aleutian low. So can our optimal precursor index also anticipate the condition in the whole basin, not just the index along the coast? So in the top row here, I'm showing the composites of the sea surface temperature, sea surface height, and sea level pressure 8 months past the peak of that optimal precursor index. And in the bottom is the panels that we just saw before. These are the composite corresponding to the maxima of sea surface temperature along the U.S. West Coast. And so there is a very good correspondence between the two sets of panels, indicating that this condition in the tropical Pacific that are optimally related to the condition in sea surface temperature and sea surface height along the U.S. West Coast are also conducive or allow us to anticipate the condition over the whole basin. It's also instructive, okay, I will use that. Oops. So it's also instructive, just very briefly here, to look at the evolution of all these fields. Just this is for a particular case, the particular time when our optimal precursor index is maximum. So this will be leg 0. And then we look at the evolution in sea surface temperature. It shows a strengthening in the ENSO condition, and then slowly a decaying. And at leg 12, we actually see that ENSO is ready to its phase transition. And again, we see similar progressions for the other two fields. Well, the important point that I would like to make is that we can see that these conditions along the U.S. West Coast actually are not only associated with the peak phase of ENSO, but they are also start to develop during the onset phase of ENSO, and they are still present during the decaying phase of ENSO. So this study so far has emphasized the importance of the ENSO precursors, especially the meridional modes. And I would like actually, before concluding, just noticing that the meridional modes are not only important as precursors for ENSO, so for tropical interannual variability, but they have been shown to be very important also for tropical decadal variability. This is from a figure from a recent study by Di Lorenzo et al. So in particular, in the left panels, we see the correlation between the leading principal component of the low-pass filter sea surface temperature anomalies with the sea surface temperature anomaly over the whole Pacific at a leg of so 1.5 years before and 1.5 years after. So we can see that this meridional, so these decadal time scales arise from the interaction of this meridional mode dynamics and the tropical zonal dynamics of the tropical Pacific. Okay. Conclusion. Okay, just 4 quick points. We have seen that the tropical sea surface temperature and sea surface height anomaly along the U.S. West Coast are most sensitive to conditions that are not necessarily coincide with mature ENSO pattern. However, the ENSO precursors, especially the North Pacific meridional mode, appear to play a very important role in promoting ENSO growth and influencing also the US West Coast anomaly. This also shows that we cannot just rely on simple ENSO indices like Niño 3 or Niño 4 or Niño 3.4. ENSO is a complex phenomenon that cannot just be characterized by one index, but its entire pattern evolution needs to be considered. And also, we see that this meridional mode dynamics is inherently associated also with tropical decadal variability, and we can expect that decadal influences can also expect to modulate these influences on the US West Coast. Thank you.
I had two questions. One is that coastal, whatever the SST anomaly, related to PDO at all? Did you look at the correlations in time?
I didn't look at the correlation in time. Oh, sorry.
Because the SST pattern looks awfully similar to PDO.
Well, this brings back to this last point here. I think this, so ENSO and the PDO are actually intimately connected, and I think it's still under debate how, what forces what, but yes.
Second question is related to, since you are dealing with something extremely close to the coastal regions and global models, including CESM, will not do good jobs near the coast. And those biases, how do they impact the conclusions that you have? If you look at a different model, we'll get a different answer.
Yeah, so I think we probably would need to look at different models. We hopefully will have global models with a higher resolution so we can better resolve coastal processes. I think so as I mentioned before, there are two ways in which ENSO can influence the US West Coast. Most likely what we are seeing in this analysis of CCSM4 is only the atmospheric one. So I'm not sure how the coastal processes, the oceanic processes along the coast are represented. So most likely that's not a realistic simulation.
Thanks. I'm wondering about the seasonality of the response versus the seasonality in phase locking events. So how does that impact the inferred lag that you get?
Yeah, I haven't looked at that. That is a very, very important question which needs to be.
What's the timing sort of a maximum response in your predict and? Like in the sea surface height and sea surface temperature off the west coast, is there a particular seasonality where that really is amplified?
Yeah. I haven't looked at that. Yeah, so but it's on the list. It's very important.
Thank you, Antonietta. Our final speaker for the session, not least, is Samantha Stevenson, who's going to talk about methods of uncertainty in quantifying climate teleconnections in climate models.
Microphone adjustment here. Hi, so it's great to be here at the CLIVAR Summit, and I'm excited to talk to you this morning. So the title of my talk might be a little bit of a misnomer because I'm not going to go into uncertainty quantification per se. As I was going through the teleconnection literature, I realized that there's so many unanswered questions still outstanding that I thought it would be more informative for this session to just go through some of the issues that relate to uncertainty quantification. So I'll be presenting a combination of both teleconnection results from the literature and then also some work that I've been doing on modulation of impacts of ENSO and other modes in collaboration with people at NCAR, so Betty Autopleasner and John Fasulo. Okay, so we've heard a bit about various types of teleconnections. So they come in many varieties. I just wanted to show the overall teleconnection patterns that are associated with three major modes. And these diagnostics come from the NCAR Climate Variability Diagnostics Package, which I also wanted to put in a quick plug for. It's an online tool that you can use to conduct quick and dirty diagnostics on any climate model or observational package you're interested in. So I highly recommend checking that out. Okay, so this is just the teleconnection pattern in SST and surface air temperature over land and sea level pressure and contours during the wintertime of an El Nino peak. So we see this deepening of the Aleutian low that's been mentioned in previous talks. And also there's just some interesting temperature structure over land in terms of the El Nino teleconnection. This is a spatial pattern of SST associated with the PDO. As Antonietta just mentioned, they're intimately connected, ENSO and the PDO, and in fact the spatial patterns of SST are highly similar between ENSO and the PDO, although there's somewhat larger temperature loading in the North Pacific associated with the PDO relative to ENSO. And then finally, the spatial pattern of SST associated with the AMO is pictured here. So this is, all of these are using the ERSST version 3 data set, and I'll get back to this question of observational uncertainties towards the end of the talk. But the AMO hasn't been mentioned yet. It's the Atlantic multi-decadal oscillation, so it has the largest loading in the Atlantic. And this is what it looks like in the modern. I think actually Alyssa mentioned the AMOC, so this is this surface expression of related to the AMOC. The AMO and the AMOC are intimately related as well. Okay, so these are the modes that I'm going to be talking about in terms of teleconnections. And how well the models generally do. Well, they do pretty well, all things considered. So this is just an illustration of the performance of the CESM with respect to the ENSO teleconnection pattern. And so up top is the correlation of precipitation in colors and 850 hectopascal winds in arrows with Nino 3.4 in the ERA interim reanalysis. And so you can see that there's more enhanced rainfall over the central and eastern equatorial Pacific. There's enhanced rainfall over the western U.S. There's suppressed rainfall over the Southeast Asian monsoon region and parts of the Amazon basin. And all of those features are actually picked up by both the CESM and the GFDL ESM2M, which is the right-hand panel on the bottom there. So these are two large ensembles that were performed with two different state-of-the-art coupled climate models. And so we're at the point now where we can start to really use these models for regional climate assessments in a stakeholder relevant context. So I just wanted to, before I get into all the things that are wrong with the models, just highlight that they do pretty well, all things considered. So models do capture some of the features of PDO teleconnections as well. So it's a paper that came out a few years ago discussing the CMIP5 ensemble. So this is a slightly older model generation than the figure on the previous slide. So this one is the CESM1 and the ESM2M. So those are very new. These are what was used in the previous IPCC report. So up top is the observed surface air temperature on the left and precipitation on the right, regressions over, I think, the late 20th century. And down on the lower two panels is the same thing for the ensemble mean in the CMIP5 projections. So you see the observed warming in the northern and western tier of the U.S. and the cooling in the southeastern. And that's picked up by the majority of the CMIP models. Where we don't do as well is in precipitation. So in general, we do better in terms of temperature impacts than precipitative impacts. So it's a little bit hard to see in the colors here, but in observations, there's a larger drying than is picked up by the CMIP5 ensemble. So in general, we have to be a little bit more careful about attributing precipitation teleconnections to these modes, which makes sense because precipitation is a more difficult field to simulate than temperature. So then moving to the AMO, this is where everything kind of falls apart. So this is just in the same paper, regressions of precipitation over land and temperature over the ocean during the boreal autumn for the 20th century on the AMO index. And the observations are in the upper left-hand panel. And so you see drying over much of especially the eastern U.S. And if you look at the model patterns, so all the other panels are different CMIP5 class models. You see entirely different patterns, both in precipitation and in temperature. So the AMO appears to be something that models are not capturing as well as either ENSO or the PDO. So that's another caveat that we might want to keep in mind as we move through the rest of the summit discussions. And then I just also wanted to point out that the previous slides I presented are the remote teleconnections to these modes. If you're trying to think about the changes to impacts, particularly under climate change and so forth, what you want to know is both the teleconnection pattern and the amplitude. And so the amplitude of climate modes is something that we don't always get right as well. So this is just the ENSO, the NEO 3.4 power spectrum in the CMIP-5 historical simulations from the IPCC report. And so the solid lines, or the darker black lines are different SST observational products. And the 2 to 7 year ENSO band is highlighted here. And you see that there's a huge scatter in the amplitude and in the width of the spectral peak in a lot of these CMIP-5 models. So the amplitude is not as reliable as the teleconnection pattern in many cases. The same goes for the AMO. Again, the observations are shown in black here, and then these are all different CMIP-5 class models. And so the AMO amplitude varies dramatically. It's a lower frequency mode than ENSO, and so if you're looking at this in a historical simulation, then you have an issue of sample size. So you know the number of oscillations in the AMO that you get during the 20th century is going to be smaller than for ENSO. So to some extent you expect larger scatter, but it does appear that we're kind of all over the place in terms of AMO performance in CMIP-5. So then just moving quickly to the PDO. So this is a Taylor diagram. So on the x-axis is the standard deviation. On the kind of curved lines indicate the pattern correlation between the mode in observations and in individual realizations of ensemble members. So basically you would want to be, let's see if my laser pointer works. Nope. You want to, observations are the big black circle. So in an ideal world, all of those dots would lie directly on top of the black one. But the amplitudes of the PDO in all these different model simulations vary dramatically. So that's indicated by their distance from the 0 point, the origin. And their correlations are also, no, sorry, I said that backwards. So the correlation and the standard deviation are both changing dramatically between different CMIP-5 ensemble members. So the spatial pattern of the PDO is different, and so is the amplitude. Okay, so you can read all about this in the Newman et al. Paper, which came out last year. Okay, so what does this mean for sources of uncertainty? Well, you have different models that you're trying to compare among each other if you're dealing with the CMIP. And so this is just an illustration of what structural differences among models might do in terms of changing teleconnections. So this is from the same paper. So this is just 2 different regression patterns on the PDO index from 2 different models. I actually don't know which ones these are offhand, but these are the models in the CMIP-5 ensemble which are closest to or furthest from observation. So you could consider them like the best and the worst model, I suppose. And so, in Model A, you get your nice loading over the eastern equatorial Pacific. It looks kind of El Nino-like. You have the cooling anomaly over the Kuroshio extension. And some of those features show up in Model B, particularly in the North Pacific, but the eastern equatorial Pacific looks entirely different. So depending on what physical parameterizations are included in the model, what resolution, how it does in terms of mean state, that can dramatically affect the representation of teleconnections. And then this is important to think about for CLIVAR because these are things that we can start to construct process-level diagnostics for. So this is moving back to ENSO. I like this figure because it illustrates some of the major feedbacks that are relevant to the ENSO cycle. You can actually start to constrain using observational data. So for example, the Bjerknes feedback on the top, so that's essentially the sensitivity of SST anomalies to wind stress. And so in all 3 panels, the black dot is observations and the red and blue dots are different models. And so we're underestimating the Bjerknes feedback in a lot of the CMIP models. So same thing for the surface fluxes. So surface fluxes feedback in panel B. So that's the feedback between SST and latent heat flux or evaporation. And so again, it looks like observations, in observations, that feedback is much stronger than in a lot of the CMIP models. So we can think about that, like maybe if we improve our evaporation data sets or we try to understand what's leading to these changes in sensitivity, then that could be helpful. And then the same thing for the shortwave feedback. So that's damping of SST by just emission of shortwave fluxes. So there are process-level diagnostics that we can come up with and try to understand where these changes, these structural differences in teleconnections are coming from. But then what I wanted to spend the last part of the talk on is how models can help us understand internal variability. And so this is something that modeling centers have been moving towards in the past few years. There's several different ensembles. I already showed you a couple figures from two of them, so the CESM large ensemble and an ensemble with the GFD-LESM2M. So those each have 30 members, so 30 realizations of the 20th century and of the 21st. There's a mitigation ensemble, again with the CESM, so that looks at RCP 4.5 instead of 8.5. But then finally, we also have the last millennium ensemble. This is another big ensemble, but it covers the entire 850 to 2005 period. And so these are really interesting toolkits because you can either look at internal variability over the historical period or actually multi-centennial variability to start to understand what the kind of unforced or naturally forced long-term modulations to teleconnections, which are then relevant for your process studies and whatnot. Okay, so what does internal variability actually look like? So moving back to the CESM large ensemble, you can see that it can be decently large. So in the upper left-hand panel is again the composites for DJF of peak El Nino in SST and sea level pressure. And then the other three panels are the same model, so the CESM, and the only difference is initial conditions here, so 3 ensemble members. And you see, particularly over the North Pacific, there can be substantial differences in the SST and the sea level pressure pattern. So basically, this deepening of the Aleutian lows associated with El Nino can be just different over different realizations of the 20th century. And so that could be because ENSO is behaving differently, maybe. It could be because there's some kind of stochastically driven atmospheric mode that happens to be more or less active during that period. We don't fully understand the processes that are leading to this. And it can be pretty important for the AMO as well. So just to show you the SST pattern that's associated with the AMO, again in the CESM large ensemble, so ERSST is in the upper left-hand corner. The AMO spatial pattern, not even the atmospheric impacts now, but the spatial pattern of the AMO itself is pretty substantially different among 3 different ensemble members. So, again, this is a low frequency mode, so you do expect a high degree of internal variability on these time scales. But that's kind of important if you're trying to compare 2 different historical simulations with 2 different CMIP5 models. It might not be that the structural uncertainty is explaining all of those differences. It could also be just internally generated. And same deal for the PDO. So I will note that these are 2 ensemble members from the CESM large ensemble. And I wanted to note that the differences between these ensemble members are actually smaller than the structural differences that were seen in the other plot that I showed you before. So at least for the PDO, it looks like structural differences might be more important than internal variability. But I would say this is still kind of an open question for a lot of climate modes. Okay, so I wanted to just illustrate in 2 minutes the utility of large model ensembles for understanding how long-term variability in teleconnected regions is driven by changes to climate modes. So just as a quick example, so we have droughts that happen in the southwestern U.S. So this is an index of drought called the PDSI. And you have, in the last millennium ensemble, this ensemble that covers 1,000 years, you can actually start to associate the properties of drought on multi-centennial timescales with the properties of ENSO. And when you do that, you see that if you change the amplitude of ENSO, you change the properties of drought. So I'm not going to get into all the details here, but basically the point is that droughts last for different lengths of time on average in the CESM. So the brown ones are longer and the green ones are shorter in the top panel. And then the bottom panel is the change in drought persistence during 200-year periods when you have stronger ENSO. So if ENSO is stronger, your droughts in a lot of teleconnected regions like Australia, like the southwest US, like parts of Africa, they're going to be shorter. And droughts tend to be longer in other places like Mexico. All right, and so this is really important for trying to look at intermodal comparisons in terms of climate change projections, because it implies that, as I think Dan pointed out, changes in variability can be really important for changes in the persistence and the risk of drought. So we expect that drying will occur in the 21st century in a lot of regions. So these are the differences in 21st versus 20th century soil moisture for the CESM large ensemble. So the southwest U.S. dries. But the risk of drought doesn't necessarily increase in exactly the same way as the mean state changes. So this is just the amount of time spent in drought conditions. And you see that there's brown on the lower panel there, so that's the difference between 21st and 20th century, and the percent risk is up top. So the risk increases over a lot of the Southwest U.S., but that pattern is very different from what you see in just the mean drying trend. So we need to understand both variability and mean state changes, basically. Okay, so I'm a little short on time, so I'll just go through my conclusions really quickly. So teleconnections are influenced both by coupled modes and then coupling with the atmosphere, the ocean, and the land, impacts from external forcing, and internal atmospheric variability. Models get some teleconnections better than others. Both structural differences and internal variability are important for intermodal comparisons, and we should run big ensembles to understand all of these things. So thanks very much.